Welcome, everyone. I'm delighted you were able to join us for today's Mineta Transportation Institute Research Snaps webinar. My name is Hillary Nixon, and I serve as the Deputy Executive Director for MTI. MTI is the U.S. Department of Transportation-funded University Transportation Center at San Jose State University. Our mission is to increase mobility for all by improving the safety, efficiency, accessibility, and convenience of our nation's transportation system. During today's webinar, if you have any questions for our presenters, you can submit them through the conference Q&A or chat feature. We are recording this webinar, and the link to view it will be available shortly after the webinar on our website and social media pages. The focus of our webinar today is a recently completed research project funded through our Caltrans research program. The objective of this study was to investigate trends in primary pavement materials unit prices over time and develop guidelines for selecting unit price values for future maintenance and rehabilitation as part of life cycle cost analysis. It gives me great pleasure to introduce today's speakers, Dr. Chang-Mo Kim and Dr. Ghazan Khan. Dr. Kim is a project manager at the University of California Pavement Research Center at UC Berkeley and Davis. He is also part-time faculty teaching transportation engineering in the Department of Civil Engineering at Sacramento State University. Dr. Khan is an associate professor in the Department of Civil Engineering at Sacramento State, where his teaching and research focuses on transportation engineering, traffic operations and safety, geographic information systems, and statistics. I want to thank you all for joining us, and we will turn it over now to Dr. Kim for the presentation.
Thank you, Hillary. Good morning, everyone. So I'm going to start my presentation today, and Professor Ghazan Khan is going to help me in the middle of the presentation. So this research task was sponsored by Caltrans-funded and done by Sac State's University through Mineta Transportation Institutes in 2019 and 2020. So before I start my talk, I appreciate Dr. Hillary Nielsen and Caltrans task manager Patrick Stafford for their support and collaboration. I'm going to read this presentation today, and Ghazan will help me as we move. Sorry. Okay, the overview. The presentation will cover the background, research objectives, and scope, data collection and analysis results, model developments and validation, case study, and summary conclusions. And Q&A time will be followed by our presentation. So brief background about the life cycle cost analysis in Caltrans. Caltrans use LCCA to compare the life cycle cost of design alternatives and select the most cost-effective option for highway construction and rehabilitation project from the early 2000s. Caltrans updated LCCA procedure manual and launched the California customized LCCA software called the Real Cost 2.5 California version in 2013. If you are not familiar with the Caltrans LCCA procedure or Real Cost software, simply Google Caltrans LCCA. You can easily find the most information on the Caltrans LCCA website shown on this link here. So this flowchart shows the Caltrans procedure of LCCA. The life cycle cost consists of agency cost and the user cost, and agency cost include the direct and indirect construction costs such as pavement cost, traffic handling, and supporting cost. Road user cost is calculated from the road user time value, excuse me, due to additional delay, excuse me, caused by the lane closure during construction. My research focused on the calculating material cost for future maintenance and rehabilitation in LCCA. The material costs are often up to 60% of agency cost of a highway project. The current procedure Caltrans LCCA procedure used the uniform unit price in calculating future maintenance and rehab project cost. So our research objective were investigate the trend of payment unit prices in the past years, and we developed the statistic models to better predict the payment unit prices for future M&R project to support the LCCA for Caltrans highway project. So we collected the unit price of the pavement material items used in future M&R cost calculations in LCCA, not the actual project, the future M&R cost calculation in the LCCA. So certain pavement items for the past 20 years were included in the data set collected through the Caltrans contract cost database. So we select the two most popular pavement materials, joint plain concrete pavement, JPCP, and hot mix asphalt type A, the HMAA. And group the material unit price by districts and pavement climate regions to check the variation of unit price by project location. The neither significant differences were statistically found in the unit price by districts nor the climate regions. So we assume project locations do not affect the unit price, and we did not separate them by project location in the future steps. The unit price shows a significant variances depending on the project size, determined by the quantity of materials, unlike the project location. Small projects using the low quantity of pavement material show higher unit price than the large size projects. I know some of you have experience and well understand this situation. For each pavement material, four project categories, small, medium, large, and extra large size projects were determined by the quartiles 25, 50, and 75 percentiles of the corresponding materials quantity of the project. And this table shows the maximum quantity of the pavement material in LCCA by the project size. For example, the project using the HMAA equals or less than 300 tons are categorized in the small size project, and the project using the HMAA over 4,500 tons are categorized in extra large size project. And each material has a different quantities to define the small, medium, large, and extra large projects. And this table shows the average unit price of pavement materials grouped by project size. For example, the average HMAA unit price or $591, and for the small projects, and then $104 for large projects. There are about like 6 times differences. The average unit price of the small projects are 6 times higher than the average unit price of the extra large projects. So similar differences were found in the most pavement materials in the table. So these two plots shows the average unit price change over the years by the project size. For both JPCP and HMAA, the average unit price shows a fluctuation over the years for the small size of a project, but steady increase over the years for the larger size projects. The larger size project shows less variation of the average unit price, as you see in the plots. So, and the other hand, 10 socio-economic parameters of the past 20 to 50 years related to pavement unit price were collected and analyzed, like gasoline prices, like population, consumer price index, vehicle registration, vehicle miles traveled, and other socio-economic parameters. Some socio-economic parameters shows the downturns over the years. For example, the crude oil price shows the deep downturns in 2009 due to the economic recession and 2015 due to the excessive oil supply. However, some other parameters does not show decline, but show increase, like California population, showing in the right side of the plots. So we check the correlation among the socioeconomic parameters. So correlation among 10 socioeconomic parameters were calculated, and the highly correlated parameters were removed to avoid the correlation bias in the modeling process. The 4 socioeconomic parameters are finally chosen. Those are the crude oil price, California population, state expenditure in transportation, and total California vehicle registration number. They are selected as the variables in the modeling in the next step. And the modeling development procedure. So first, we use the time series analysis of the socioeconomic variables. We predict the future values of the socioeconomic variables using the ARIMA, the auto-regressive integrated moving average method. And ARIMA smoothen the fluctuation for downturns and predicts the future values of each variables. As an example, for both crude oil price and California population, the future predicted values from the ARIMA were lower than the value from the simple linear regression of the past value without considering the time-associated effect. So as you see here, the blue lines are the actual value in the past, and the red line is the predicted value in the future in the time series models. But the blue dash line, these are the predicted value from the simple linear regression model. So this one doesn't really consider the effect of the time series, but the ARIMA model consider the smoothen the fluctuations and downturns over the past years and predicts the value for the future 50 years. And time series analysis results show the future predicted value for both vehicle registration and transportation expenditure, state expenditures. Will be higher, the future values will be higher than values from the simple linear regression in the future due to the time associated effect. So this one here is, for example, the California vehicle registration. The time series model predicted the higher value in the future than the simple regression estimates. Next step, we developed multiple regression models. So we use 4 independent continuous variables that selected the socioeconomic parameters in the previous steps, and the 1 independent binomial variables, the project size, the the dependent variables of each multiple regression model is the future unit price by the project size. So the R-square values of the multiple regression models are between 0.5 and 0.9, as shown here in the yellow highlights. That indicates the models statistically well predicts the unit price of the pavement material by project size. The table shows the coefficients of each models for each variables. And this plot shows the unit price of JPCP and HMAA predicted by the project size for next 50 years from each model. When the predicted values of the socio-economic variables and the project size are chosen for the future year, for example, 2050 or 2065, a future unit price is calculated in the corresponding models. So these are the past unit prices, average unit prices, and these are future average unit prices estimated in the multiple regression model. And we did the one case study. The two separate LCCA were executed by using the uniform unit price without consideration of the project size and activity years. And second one is second LCCA used the predicted unit prices by the project size in the corresponding activity years. So we had the two alternatives for the rehabilitation projects over 9.6 lane miles in 2020. Alternative one, the HMA rehab with a 0.65 feet thickness with a 20-year design life. And alternative two was the JPCP rehab 1.0 feet with a 40-year design life. For both alternatives, HMA and JPC rehab, the future unit prices were predicted in the models and compared with the uniform unit prices in the net present value, NPV. In the future years, the predicted unit prices become higher than the uniform unit prices for both alternatives. For example, year 2061, uniform unit price of HMA is 183, which is same as the year 2020 when we use the uniform unit price. But when we use the predicted unit price of HMA in the future year, 2061, the unit price of HMA is $568 per ton. So these values are predicted from the time series and the multiple regression models. And net present value, so this with a 4% discount rate, the uniform unit price of the HMA in year 2061 is going to be equivalent as $37 on the net present value, as where the predicted unit price is going to be $114 in net present value. So there we can see there's a big differences even in the net present values for the HMA. And the same situation in the JPCP as well. So JPCP, the unit price of 2065. By the way, the net present value unit should be the cubic yard. I'm sorry, this is a typo. So 2065, the $42 for cubic yard with the present uniform unit price. But when we use the predicted unit price of JPCP, then the NPV value will be the $143 per cubic yard. Okay, the summary and the conclusions. The trend in the material unit price were explored by the project size, which the districts and the climate regions, and the project size. So there was no significant difference in the unit price by the project locations, but there is a significant difference in the unit price by project size. So we categorize the projects by the project size, from small to extra large project. And we developed the multiple regression models to estimate the annual unit price of each pavement materials by project size for next 50 years from year 2020 to 2069. In LCCA, long-term prediction include the uncertainties due to the unexpected economic trends and the industry demand-supply condition. The models were good with a reasonable prediction that overcome the sudden changes due to economic downturns, for example, the 2008 economic recession. The R-square values of the different variables were in the range between 0.5 and 0.9, which are acceptable, practical. The prediction models by the way, the prediction model of the roadway excavation, class 2 and 3 aggregate base, HMAA, rubberized HMA, JPCP, and laying concrete base were adequate, showing the reasonable result with a good prediction. By the way, these items, material pavement items, are popular and hundreds of data are found in the past 20 years database. On the other hand, the prediction models for class 2 aggregate surface and HMA all open graded, OGFC, open graded friction course, and RHMA, open graded, and JPCP, rapid setting concrete. Those are like the rarely, those materials are rarely used in the projects in the past years, and we had only like several dozens of less than 100 projects showing in the past years, and they are contrary to the normal expectation, and we are not recommend for use of those models, the models for those pavement materials. The economic recessions and the global pandemic can have a significant unexpected influence on the variation in material unit price and project cost in the future. Nevertheless, the data-driven scientific approach as described in this research reduce the risk caused by such uncertainties and enable practically reasonable prediction for the future. The developed model can be implemented into enhancing the current LCCA procedure to predict more realistic unit prices and the project costs for the future M&R activities. These are the this is the last slide, and I prepared for this presentation today. So I'm gonna hand over this talk to Hillary. Thank you.
So, Chandler, thank you so much. That was super interesting, particularly from someone who isn't a pavement expert. We do have a clarifying question that I'm hoping you can talk a little bit about, because I think it probably goes back to how you set up and the decisions that you made in terms of the two materials you focused on. So you focused on the JPCP and the hot mix asphalt. Well, there was a question whether recycling options were considered. Specifically, I believe it's cold in place recycling and full depth reclamation. And I'm wondering if you could talk a little bit about the reasons why the research focused on the two materials you did, as opposed to this other procedure, which I know is used in pavement rehabilitation.
Thank you, Hillary. Yeah, that's a very good question. So let me go back to the slide, showing the number of projects observed in the data observed in the past 20 years. So as you see here, the number of projects for the HMA type A, it has over 2,000 projects over past years. And the JPCP has about 200, 300 projects in the past years. Those two pavement materials are most popular pavement items for flexible pavement and rigid pavement in California. So that's why I picked these two materials and the examples. But by the way, the report shows the trends and the model process for each pavement materials. And in the question, was FDR and CIR, right? The full depth reclamations and the cold in place. So those are relatively newer pavement items, and Caltrans do not have a number of projects using those materials. And the Caltrans current LCCA procedure manual do not reflect those items in the LCCA procedure. So that's a good approach. Those are good approach to collect more data on those items, and then include in the pavement LCCA procedure with this kind of the approaches. So you're welcome.
Thank you. So a couple other questions. So when you think about the work that you've done, an important element of all of our research is to make sure that it's practical practical and it can be implemented. So if you could talk a little bit about how do you envision Caltrans engineers using this research when they're conducting a practical LCCA?
Okay, I'm sorry, I had a little lag and my internet connection. So that's a good question as well. So Caltrans engineers, they rely on the Caltrans LCCA procedure manual and the real cost LCCA software. So when Caltrans engineers or when the consultant or the government engineer run the life cycle cost analysis, the unit prices are very important, the fundamental inputs to calculate the project cost in the future M&R projects. So the Caltrans LCC procedure manual can guide how to choose, how to select the unit price in the future years of the M&R projects, and how the real cost software can provide the option to change the unit price in the future and those guidelines. So in the reports, we generate the lookup tables, the unit price of the future 50 years on each materials we provided here today. So like 13 major pavement materials, unit prices are generated in the appendixes in the report. So users simply can look up the unit price on the specific year and the specific project size and use those unit price in their life cycle cost analysis on the sideway, or they can use the that value in the real cost software. So it would be good to integrate those function, our models in the real cost software directly.
Okay, well, and I think that actually brings me to another kind of a follow-up question. When you talk about the lookup tables and the information that you have in the report to allow engineers to do these LCCAs, how long do you think the models that you've developed will remain valid? I'm presuming there'll be a need to to periodically update them, and how easy will that be to do given the structure you've put in place?
Kajan, would you like to answer on this question? Would you like to help me?
Yeah, I'm sorry, I didn't get the whole question. Could you please repeat that?
Absolutely. So kind of thinking about, you've set up this model, you've looked at the prices, unit prices to date, but how long do you think these models will remain valid? Will there be a need to periodically update them? And given what you've provided in the report for users, how easy will it be to do that?
Yeah, that's a good question. I mean, I always, whenever we have statistical models and we develop those, I like to quote famous statistician John Tukey, who said, all models are wrong. Some are just more useful than others. And it's kind of true for these models as well. These models are based on data. And some of the variables were available for longer periods of time. Others, we had shorter time frame of data available. Hence, there is always need to incorporate new data. As we go into the future, we are going to have more project data available. And we had some internal discussions about these to understand and realize, what could be a reasonable time frame. And somewhere between 2 to 5 years sounds like a good time period in which we can take newer project data, incorporate those into our current models and revise them so that they can be used for future. Obviously, if you leave these models just as is for more than, let's say, 5 years of a time, the results might not be as useful or as accurate as they are at this point in time.
Great. And we probably have time for one more question. I have another question that came in, and it's actually one that I find really interesting because you brought up in your presentation that there were these huge, what was it, like in some cases, a 6 times higher cost for smaller projects as opposed to larger projects. And I think I intuitively understand that. But could you talk a little bit more about why pavement materials cost more in smaller size projects? And maybe even kind of talk about, well, what do you think maybe a solution for that could be in the context of transportation engineering, rehabilitation, maintenance projects?
Okay, this is Changmo again. So I can answer Hillary's the questions Hillary just described. So this is more like the nature of the pavements and construction projects. So like I can give you one simple example. When you buy your bottle of Coke on the gas station, then you pay like $2. Like, but when you go to the like wholesale warehouse and then buy like case of the Coke bottles, then you're gonna pay much less price, unit price for buying the quantity. So in the same situation, for example, the HMAA, so they need to make the batch plants on the project sites, and then they're gonna mix the asphalt concrete mix, and they need to build a new the batch plant near the project site. If they're gonna use like only 100 tons of the HMA, then the unit price should be higher because of all the infrastructure to prepare those materials. But when you use like 100,000, like 1,000 or 5,000 tons of HMA, then all the facilities prepared for the HMA materials is going to be like more effective. That's why the unit price of the pavement material by project size has a huge variation.
So probably a silly follow-up question. Again, I'm not a pavement person. Would there be any value in like cluster buying? So you make a bulk buy when you know that you are going to have like a dozen small projects or something like that. And then you could take advantage of this economic efficiencies.
Yeah, that's the good idea. That's a very good idea. I never thought about that approaches, by the way. Yeah. So the HMA has to be a certain degree of the temperature. Like it has to be like 450 Fahrenheit when they be installed, built in the pavement surface. So it's very crucial the maintaining the temperature of the high temperature to provide the quality of the pavement and bonding quality. So it's kind of hard to prepare the HMA like as a cluster and then applying the project A and project B and project C tomorrow, today, and day after tomorrow, such like that. So it has to be very on time and right temperature like that. But the same situation for the other rigid pavement material as well. So yeah.
Interesting. Again, non-pavement person.
Yeah.
So
yes.
we hit our half-hour mark. In fact, I went a couple minutes over. So to our attendees, thank you. The final report from Dr. Khan and Dr. Kim's work will be published to our MTI website fairly soon, in fact, and we will certainly send it out to all registered attendees. A copy of this presentation, recording, will be available. And we will also distribute it widely through Caltrans, since this was a specifically requested research project from Caltrans. And I encourage you, if you haven't already registered, to register for our next Research Snap presentation on September 17th, looking at the kind of the history of the quintessential American road trip. So thank you very much for attending. Dr. Kim, Dr. Khan, thank you so much for your expertise. And we will all see you again on a future webinar. Thanks, everyone. Bye-bye.
Thank you. Bye.